All right. Are you ready to heat things up in lab? Because that's what you're going to be doing in today's experiment. Today's experiment is on the subject of endothermic and exothermic reactions. So we're going to have to start right off the bat by defining a whole bunch of terms. So let's get started. The first of the terms you need to be familiar with is energy. Energy is the ability to do work. It has units in the SI system of joules, and in the metric system it has units of capital C calories and lowercase c calories. A lowercase c calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So if you remember, a gram is about the mass of a paper clip. Degree of Celsius isn't that big a temperature change. So a calorie is a very small amount of energy. So small, in fact, that it would make our the energy content of our food look huge. Therefore, you'll see on food packaging that they use capital C as opposed to lowercase c calories. Capital C calories are equal to 1,000 lowercase c calories. Joules in the SI system are also a very small unit of energy. Turns out that .184 joules equals 1 lowercase c calories. So a joule and a calorie are both units of energy, but they're both very, very small. Your class, because a lot of you are going into the medical profession if you're in this class, they will focus largely on using calories. In the chemistry lab, I tend to think and work in joules. So energy is the ability to do work. First law of thermodynamics otherwise known as the law of conservation of energy states that energy can be neither created nor destroyed. One of the things that you may have heard about a chemistry law is in order for a law to be useful, it has to be predictive and it has to be able to be expressed in the form of a mathematical equation. That's where chemists and physicists are way superior to those biology folks, right? There's no laws that are just statements of things that may or may not have happened, right? There is only laws that can be put into mathematical form. So how can we put the fact that energy can't be created or destroyed into mathematical form. We do it like this. We say that the change in the energy of the universe is equal to 0. For the first time here, I've probably used a triangle. Whenever you see a triangle in chemistry, and we'll use lots of them before the end of the semester, it's shorthand for change. So the change in the energy of the universe is equal to 0. What that means is that every single chemical process can be thought of as a zero-sum game when it comes to energy. When we talk about energy as chemists, we divide the universe into two parts. We divide it into the surroundings and the system. The system is what we care about. The surroundings is everything else. More formally, it's everything in contact with our system. Since the change in the energy of the universe is equal to 0, and we divide the universe into two parts, the surroundings and the system, that means that any change in the energy to our system has to be balanced out by an equal and opposite change in our surroundings. In other words, the change in the energy of our system plus the change in the energy of our surroundings has to be equal to 0. At the risk of dragging absolute value signs into a perfectly good chemistry class, oh, I don't even need to do that. We'll just write it this way. The change in the energy of our system is equal in magnitude, but opposite in sign to the change in energy of our surroundings. Ooh, why in the world did I put a negative sign there? It has to do with this summation, right? If we're going to have a net change for the universe equal to 0, then that means one term has to be positive and one term has to be negative at all times. Otherwise, you'd wind up with a positive number or a negative number. That means in energetic processes, that positives and negatives denote the direction of energy flow. Let's take the simplest example I could possibly think of an exchange of energy between two systems. I have a glass containing 50 milliliters of cold water. At 20 degrees Celsius. I have another glass over here that contains 50 milliliters of hot water, quote unquote, and we'll say our hot water is a scorching 40 degrees Celsius. Now, it doesn't take a rocket scientist to know what's going to happen when you mix these two waters together. If you took your cold water and poured it into a glass, and your hot water and poured it into the same glass, you'd wind up with 100 milliliters of water at 30 degrees Celsius. Common sense, right? Let's break down what had to happen, though, in order for those two waters to arrive at the same temperature. Well, our cold water obviously had to warm up, and our hot water had to cool down. Well, how does something warm up? It gains heat. In this scenario, very specifically, it had to gain 50 calories of heat in order to reach 30 degrees Celsius. Well, if it had to gain 50 calories of heat, what had to happen to our cold water over here? What had to happen to our hot water? Our hot water had to fall to 30 degrees Celsius. How does something lower its temperature? It loses heat energy. So our hot water over here actually had to lose energy, and specifically it actually had to lose 50 calories of heat. Of heat energy in order for our mixture to have a net temperature of 30 degrees Celsius. So let's apply that in mathematical terms to our first law of thermodynamics. The change in the energy of the universe is equal to 0. And here our universe consists of two parts. We've got what we'll call cold water, and we've got some hot water. So the energy change experienced by our hot water plus the energy exchange experienced by our cold water has to be equal to 0. We know that our cold water had to gain 50 calories and our hot water had to lose 50 calories. Well, if our hot water was losing 50 calories of energy, what do you think the sign should be? It should be negative, right? Anytime you lose things, it's negative. Our cold water had to gain 50 calories, so we call its gain a positive change in energy. And 50 positive plus 50 negative is 0. So the change in the energy of the universe was 0 because our cold water gained energy, and all that energy gained from our cold water came from our hot water. Thinking about our examples helps us define a couple rules here. Let's deal with our hot water first. If we view the hot water as the system, in other words, what we're studying, then it lost energy. Whenever our system loses energy, it is said to be undergoing a exothermic process. Specifically, since we're talking about specifically here we're talking about heat energy. So it's said to be an exothermic process whenever it loses heat energy. Whenever you have an exothermic process, the sign of heat flow will be negative. The opposite is going to be true for our cold water. If we view the cold water as our system, our cold water gained heat, cold water gained energy, cold water gained heat, gained energy. And what did we say the sign would be for it? We said the sign would be positive. And we would refer to the process as endothermic. You guys really need a keyword to write down. My apologies for not asking you one sooner. Why don't you write down heat wave, the Flash villain heat wave, even though they've turned him into a kind of semi-superhero on DC Legends of Tomorrow, and then they've merged him with Kronos, which was really, really silly and bizarre. But at any rate, heat wave, the Flash villain. All right, let's put the terms exothermic and endothermic in terms of a chemical reaction, or in the context of a chemical reaction. I have a flask here, and in that flask, I'm carrying out the reaction of hydrogen and chlorine gas to produce hydrogen chloride. If I touch this flask, it would feel hot to the touch. Because as that reaction occurs, the reaction produces 185 kilojoules of heat. If we look at the reaction, we have hydrogen and chloride reacting to yield hydrochloric acid, or hydrogen chloride gas, and 185 kilojoules of energy. So we have a reaction that's producing energy, Because we define this as the system and we're the surroundings, this feels hot to the touch. When you have energy as the product of a chemical reaction, the reaction is said to be exothermic. If we think back to our first law of thermodynamics, that energy can't be created or destroyed, the question you should be asking yourselves is, if our chemical reaction is producing 185 kilojoules, where is that 185 kilojoules coming from? Good question. That was just the question I'd hoped you'd ask. It's coming from what's known as the internal energy. Just a second here. It's coming from the of the hydrogen and the chlorine. Inside every substance in the universe, there's energy. This energy is stored in the form of kinetic and potential energy. Anything that exists as matter has energy to it to some degree. So let's define internal energy real quickly. Internal energy. The internal energy of a substance is the sum of the kinetic and potential energies of a system. Internal energy, the sum of the kinetic and potential energies of our system. Real quickly, walk down memory lane here. Kinetic energy is the energy of motion. Potential energy is stored energy. And it's energy due to positions. In the context of chemistry, we find potential energy and energy due to the positioning of atoms or molecules. Or it's the energy stored in chemical bonds. Or the energy stored in forces. And I spelled potioning. It's like I'm Professor Snape there. Positioning. So potential energy is stored energy. And in terms of chemistry, we find potential energy in terms of the energy of position, and the energy stored in chemical bonds. So we have potential energy and we have kinetic energy. So we've thrown three new terms at you: internal energy, kinetic energy, and potential energy. And now I want to clean up just a little bit here. What I have is I have an energy diagram here. This energy diagram is a graph. It has energy on the vertical axis, time or reaction progress on the x-axis or the horizontal axis. At the beginning of the reaction, you have your reactants, and they have a great deal of internal energy in this reaction. Much more internal energy, as you can see from the graph, than do our products. The amount of energy stored inside our hydrogen and chlorine molecules is greater than the amount of energy stored in our hydrogen chloride molecule. And a matter of fact, their difference in energy is, guess what? That 185 kilojoules there that it releases. So the energy that it's able to produce comes from the internal energy of the hydrogen and the chlorine. Therefore, even though this feels hot to the touch, even though energy is a product, the internal energy of our system has decreased. Our system has lost energy. So whenever energy is a product, it's an exothermic reaction. If you're a biochemist or a biologist, you'll write exothermic reactions like this, where you write the number and it's part of the product. It's on the product side of the reaction. However, if you're a P chemist, somebody who studies the physics of chemistry, you'll write exothermic reactions differently. You'll write your chemical reaction, and then you're going to end your reaction. You're going to treat it like a sentence. You're going to write a semicolon. You're going to write a delta H. You can think of delta H as being change in heat. Then you're going to write a negative. Why? Because we lost internal energy. Our chemicals themselves lost internal energy. So you write delta H equals a negative 185. Whenever you see a chemical reaction that has a negative sign, that negative sign means that your reaction is exothermic. So whenever you see energy as a product, or you see that your change in heat is negative there, you know you have a exothermic reaction. Let's take a look at the opposite of an exothermic reaction. But before we do that, why don't we write down Firefly, the Batman villain, who they have gender swapped on Gotham. Firefly. Also one of the best G.I. Joe action figures ever, but I'm really dating myself with the G.I. Joe reference. All right, let's take a look at the reaction of nitrogen and oxygen. If I carried out this reaction in a flask and you were to touch it, the reaction would feel cold to the touch. That's because in order for this reaction to occur, it has to have energy as a reactant. It requires energy to occur. Where is it going to get that energy from? It's going to get the energy to carry out the reaction from the surroundings. Who's the surrounding? You are, because you're touching the flask. So it's taking energy from you to make the reaction go. So it feels cold to the touch. Now, energy can't be created or destroyed. So where does this 180 kilojoules of energy that we're adding to our reactant chemicals go? It goes inside those nitrogen monoxide molecules. It increases the internal energy of the chemicals. If we look at our graph again of energy versus reaction progress, we see that the nitrogen and the oxygen have less internal energy than does our 2 molecules of nitrogen monoxide. How much less? 180 kilojoules left. So this system requires the input of energy. Whenever you have a reaction where energy, usually in the form of heat, is a reactant, the reaction is endothermic. Because we're adding energy to our system, it's going to look the exact opposite way in pChem notation. If you're a biochemist or a biologist, chances are you're going to write an endothermic reaction exactly like you see it here, with energy as a reactant. If you're a pChemist, however, you're going to use that delta H notation that we saw previously, where you have nitrogen, where you write your chemical reaction, you don't write your energy, so you write your chemical reaction, then you put that semicolon in again, then you write your delta H, and even though energy is a reactant, we don't write on the reactant side, you write it here after the semicolon, but we write it with a positive sign to show that we're adding energy. So when you see a reaction written in delta H notation with a plus sign, you know that it's a endothermic reaction. So those are endothermic and those are exothermic reactions. Let's kind of come up with a little table here to summarize. Alright, so let's make our chart. We have, whoa, and now I've really botched things. Come on. We have exothermic reactions here. We have endothermic reactions here. And first thing we'll do is the sign of delta H. For an exothermic reaction, the sign of your delta H would be negative. For an endothermic, it would be positive. In the context of a reaction, RxN, by the way, is how chemists abbreviate reaction. In a reaction context, exothermic would have energy as a product, and endothermic reaction would have energy as a reactant. If you were to touch the reaction vessel, how would it feel? An exothermic reaction would feel hot to the touch. An endothermic reaction would feel cold to the touch. They use an exothermic reaction in hand warmers. They use a endothermic reaction in cold packs. Let me tweak this just a little bit here. Greater internal energy. An exothermic reaction, the reactants have greater internal energy. For an endothermic reaction, the products do. So there's a little bit of a summary of what we talked about with endothermic and exothermic reactions. A couple quick things here. This delta H, you can think of it as change in heat. Very formally, it's actually called your change in enthalpy, which is simply heat at a constant pressure. But whenever you see that delta H, if you just want to think of it as change in heat, that's fine. Also, let's throw up here, as long as we're throwing up things up here for review. Internal energy. The sum of the kinetic and potential energies of a system. Write down Brimstone. Everybody write down Brimstone. He was a person fought by the Suicide Squad back in the miniseries Legends in 1986, if I remember my comic book history, when the DC universe reset itself post-crisis. And if you understood any of that, I feel for you, because it means your comic book addiction is as bad as mine. In today's lab, what you're going to be doing is you're going to be determining whether or not a reaction is endothermic or exothermic. You're going to be doing that by absorbing by measuring the temperature of water. The reactions you're going to take, the reactions that are going to take place are going to be carried out in water. Remember, when we talk thermodynamics like we are now, the reaction and the chemicals in the reaction are always our system. That means that the water that they're carried out in are the surroundings. So, brain teaser. If the temperature of the water increases, is the reaction endothermic, or if the temperature of the water increases, is the reaction endo or exothermic. All right, so if we see the temperature of the water increase, that means our water has gained heat. And if heat can't be created or destroyed, where did the heat that the water gained come from? It means it had to come from our reaction. So that means our reaction produced heat. And according to our chart, whenever our reaction produces heat, that means the reaction is... And I'm not going to tell you. That'll be for your pre-lab quiz. You will be dealing with one really nasty chemical today. So as always, make sure you wear your goggles. Make sure you pay close instructions. Reread and read chemical instructions at all times. And that's all. Beep.